Greetings, grade 12s, and welcome to Ubuntu Academy, lessons that empower. Today we are back preparing for your June examinations if you are writing in Gauteng on the 19th of June. So we are looking at paper 2 today, and we are going to start with organic molecules, the first part of organic molecules. Now, before we do that, let us quickly go through the scope as received. Okay, as you can see under paper 2 there, the second line under the multiple choice question will be organic chemistry. Now, usually what happens is that this topic will then be divided into 3 different questions. So today what we are going to be looking is what is likely going to be in the first question of organic chemistry, which is likely going to be in question 2 of your paper 2. Right. Now, what is to be expected? Of course, just like any other topic, the first thing that you need to expect and should prepare for are the definitions. And here we don't negotiate. We make sure we collect maximum marks for every definition. And unfortunately, this is a topic that has a lot of definitions, and we have to learn all of them in order to maximize our possibility of getting good marks. Okay. Right, these are some of the definitions that you should study: hydrocarbons, homologous series, molecular formula, structural formula, condensed structural formula, functional group, saturated compounds, unsaturated compounds, and structural isomers. Now, when it comes to this one on structural isomers, you are expected to at least understand 4 different definitions, because the last part, the last bullet point is about 4 different definitions, because structural isomer on its own is a definition which you should learn, together with chain isomer, which is here, and there's also positional isomer, and there's also functional isomer. All in all, these make up the 4 definitions that you need to learn. So you need to know all the different types of isomers in terms of the definition, so that you are able to answer the question if it does come up. Right, then we move to the next part that you need to understand. These are the various types of formulae. Now, when it comes to chemical compounds, or in this case, because we are dealing with organic compounds, they may be represented using various types of formulae. So the thing is, the first type of formula that you have to learn is what is referred to as the molecular formula. Now, this is the easiest of the formulae that we are going to look at here. This one is a formula that shows the number, okay, the number of each type of atom in the compound. So basically what it does, it just tells you here there are 4 carbons and 8 hydrogens, for instance. Let's make that as our example. Okay, so let's say this would be C4H8. As you can see, this is referred to as the molecular formula. What it does, it just tells you the number of each type of atom in the compound. It says the type of atom, carbon is represented 4 times, or by 4 atoms there, and hydrogen is represented by 8 atoms. So that's what we call the molecular formula. It is the easiest or the most simple of the formulae that we're going to look at today. The second one is what is referred to as the structural formula. Now, when it comes to the structural formula, here we are going to be looking at a detailed structure showing all the atoms and the bonds between them. Okay, so this one shows all the atoms and all the bonds and how they are linked to each other. Now let's continue with that C4H8. So what would happen here is that you would have C4H8 would be an alkene. Okay, so let's do this. We'll put 4 carbons. Okay, let me put a double bond here so that we can be able to have 8 hydrogens. Okay, let's put another one here, another one here, another one there, and another one there. Okay, we'll count the number of hydrogens to see if it does match. Okay, I don't have enough space at the top. Please forgive me for putting it on the side. It's supposed to be just above the bond, not on the side of the bond. Okay, so this would be the structural formula of that molecular formula. It's the same molecule but represented by different formulae. You have to know that, and you have to remember to do that when you are required to do so in your exam. So as you can see, we have 4 carbons here, 1, 2, 3, 4, and then you have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, just like the molecular formula there. This is what we call the structural formula. It shows us all the bonds and all the atoms and how they are attached to each other. Oh, okay. I don't have enough space there. I'll have to remove some of the hydrogen bonds there. Because I want to save this, let me just make sure that we don't. Okay, there were no hydrogens here. There were hydrogen here and here. Okay, hydrogen. Make sure that when you draw your structural formula, each carbon only has a maximum of 4 bonds, not more than that. As you can see with this carbon here, it's 1, 2, 3, 4. The double bond is counted twice because those are 2 bonds there. Together with this carbon as well, as you can see, it's 1, 2, 3, 4. There are 4 bonds in around each carbon atom. Now we then move to what is called the condensed structural formula. It's quite similar to the structural formula, except now you do not show the bonds. You do not show all the bonds. Sometimes you do show a bond or two in special cases such as aldehydes and ketones. Sometimes we show the double bond between the carbon and the oxygen. But here, with regards to this one, how you draw a condensed structural formula based on the structures above, you would then check how many hydrogens are attached to the carbon, and that's what you write. You say, okay, the first carbon is attached to 3 hydrogens, and the second carbon is attached to just 1 hydrogen. The third carbon is also attached to just 1 hydrogen, and the last carbon, okay, there's a hydrogen missing there, okay, and the last carbon is attached to 3 hydrogens. So all these 3 structures that you see here, from this one, the first one, here's the second one, here's the third one, all of them represent the same compound. Of course, that molecular formula might represent other structures as well, but in this case, we are only focusing on the structures below it. So this would be your a simplified structure of an alkene. In this case, this would be a but2-ene. We'll talk about that in the next few slides. Okay, so these are the formulae that you should be able to draw when you are given the information. So you might be given the structural formula and you're required to draw or to write down the molecular formula or the condensed structural formula. So you should be able to move in between. Given one, you should be able to draw the other 2 and also be able to write the IUPAC name. We'll talk about that in the next few slides. Now here's another, I prepared this slide because I think it might be able to assist you, especially with the homologous series, the various types of homologous series. So these are the general formulae. We hardly talk about them. Even the exam guide doesn't really mention, doesn't say much about general formulae, but it's also important. Now, we use these formulae to identify the homologous series of compounds from their molecular, structural, or condensed structural formula. Okay, now basically every homologous series has a general formula. Okay, can be represented by a general formula. Now a general formula, usually we have the letter N representing the number of carbons in the compound. So the formula doesn't tell you how many carbons are there, but the number N just represents the number of carbons. Let's start with alkanes. For instance, with alkanes, the general formula for alkanes is CnH2n plus 2. What this means is that in terms of the number of carbons, the number of hydrogens is determined by the number of carbons. Let's have an example in this regard. This means if you had, for instance, 6 carbons, let's say this is C6, okay, the number of hydrogens would be 6 times 2, as you can see, 2n there, 6 times 2, which is 12, plus 2, then it becomes H14. So alkanes have this general formula. So why are we doing this? We are doing this so that we are able to see. Let's say, for instance, you come across a condensed structural formula and you're not so sure to which homologous series it belongs. If you break it down to its general formula according to the number of hydrogens and number of carbons, you'll be able to tell which homologous series that compound belongs. Alkenes have the general formula CnH2n, just like we saw earlier on. We had C4H8. As you can see, the number of carbons is 4, the number of hydrogens is 2 times 4. That's your 2N there. And then alkynes, it would be C N H2N minus 2. In an example, let's use C5. This would be H, the number of hydrogens for an alkene. If you have 5 carbons, it would be 2 times 5, which is 10 minus 2. Then it becomes H8. That would be your alkene. And then I want us to also look at the alcohol. The alcohol is a general formula CnH2n plus 1. So this means the number of hydrogens will be 2 times the number of carbons plus 1 more hydrogen. That is excluding the hydrogen that is bonded to the oxygen there, which is the functional group of the alcohol. So the plus 1 there does not include this hydrogen here. Okay, so when you see, I think the alcohols are a little bit easier to identify, because as soon as you see the OH, you are able to tell that this is an alcohol. So these are general formulae that can assist you to identify the homologous series and also to be able to draw the accurate number of hydrogens per the number of carbons. Okay, now let's move to the last 4 homologous series. We've addressed the first 4. Of course, I did not talk about the haloalkanes because they're quite similar to the alkanes. Okay, so now we're going to be looking at the last 4 homologous series, which are your ketones, your aldehydes, your carboxylic acids, together with your esters. Now, with these ones, we are going to use what we refer to as the case 2-Cho-Hock strategy. Okay, it's easier to remember that way if you memorize it that way. Case 2-Cho-Hock, and it's going to assist you in case you forget some information, especially about the last 4 homologous series. Now, this strategy is going to be used to identify or even draw structural formulae for ketones, aldehydes, carboxylic acids, together with esters. All right. Now, why is this strategy dedicated to these 4? We know that all these 4 mentioned homologous series have one thing in common, and that is they have in their functional group, they have a carbon double bonded. They have a carbon that is double bonded to an oxygen. Okay, all 4 of them have a functional group which has a carbon which is double bonded to an oxygen. Okay, then now there are other things that differentiate or distinguish them from each other. Ketones do not look like aldehydes, just like carboxylic acids do not look like esters, although they all have this one thing in common, which is a carbon double bonded to an oxygen. Okay, so now what is it that differentiates ketones from the rest of them? We know that all of them have that double. Let's look at them quickly on these blocks. We are going to be putting the functional groups of each of these homologous series. Now, ketones have this functional group. This is the functional group of ketones. Now, we know what is common in all these homologous series is this carbon double bonded to oxygen. So that is not special. It actually happens, it appears in all these homologous series. The aldehydes have this carbon double bonded to oxygen. The carboxylic acid has that together with the ester. But what makes the ketone different from the rest of them is the fact that the ketone has 2 carbons on either side of the carbon double bonded to the oxygen. So these are the 2 carbons that makes the ketone stand out from esters and also from aldehydes and carboxylic acids. Okay, hence we then say at the top there, I'm going to write that what differentiates ketones from the rest of them is the 2 carbons. Hence you see 2C there, which is part of the 2-Cho-Hock that I mentioned earlier on. This should be able to assist you, right? Then we move to aldehydes. Again, we are going to start with the functional group of aldehydes. The functional group of aldehydes looks like this. Look what is common again. There is our group of atoms which is common in all 4 of them. 1 carbon double bonded to an oxygen. But then what is it that is different between these 2? Between the ketones and the aldehydes? The ketones have 2 carbons. 1 carbon on either side of the carbon double bonded to the oxygen. Whereas in the aldehydes, there is the carbon double bonded to an oxygen, but what does it have? It has a hydrogen. Therefore, what differentiates that aldehyde is the fact that it is bonded to the double bond. The carbon double bonded to an oxygen is also bonded to a hydrogen. Hence, we put that hydrogen here. All right. So all of these will add up to the two CHOHOC that we spoke about earlier. Then we move to the carboxylic acids. As you can see, just like in the previous one, we have that group of atoms, the carbon double bonded to an oxygen. But this particular carbon is double bonded to an oxygen. It is also bonded to an OH. That is what we are going to see over there. Okay, that OH, there it is. That's what differentiates the carboxylic acids from the esters and the aldehydes and the ketones. Okay, all of them have this in common, the carbon double bonded to oxygen. I'm sure now you can see where the pattern is going. Then we have the last one, which is the esters. As you can see, once again, we have that group of atoms, the carbon double bonded to an oxygen, but what else is there is the O and the C, which is what we expect to see at the top there. Okay, the O and the C. Okay, so now that you've seen what differentiates these homologous series from each other, you can use this very same table. Now, what I usually say to learners is that before you start writing your exam, try to remember this table and write it down somewhere. It becomes part of your table of data, and then you can refer to it at any time during your examination so that you are able to differentiate between ketones and aldehydes, because those can be similar as well, together with carboxylic acids and esters. Just draw that table and then write it. It's quite an easy table to remember. Just remember case 2 CHOHOC. If you forget, because I know some learners would say they don't know where to draw the line. What you have to know is that the 2 goes with the C. Okay, so I'm just going to draw a line there quickly. The 2 goes with the C. The H goes alone. So the first hydrogen is alone, and then the second hydrogen goes with the oxygen, and then the last 2. So there's only one letter that goes alone. The first 2 characters go together. The second one is just one letter, and then the third, it's a group of 2 atoms, and the fourth is also a group of 2 atoms. That's another way of remembering the case 2 CHOHOC strategy. It works, and it should be able to assist you, especially if you're still not familiar with the last 4 of the the homologous series that we are dealing with. Then we move to the next part that you need to master before you go to the exam. It is quite a tricky one for many learners, and I hope it's not going to be too tricky for you in this exam. And this is a slide that should assist you as well. IUPAC naming. Remember, so far we know 3 ways of representing organic compounds. We can either use one of the 3 formulae that we spoke about earlier on, where we have a structural formula, a molecular formula, and a condensed structural formula. But also an organic compound can be represented by using an IUPAC name. So the IUPAC name of an organic molecule can be divided into 3 parts. Okay, it can be divided into 3 parts. The first part is the prefix, followed by the parent, and lastly the suffix of the name. So that name is divided into 3. Now let's go straight into an example in the interest of time. Now here's an example of a structural formula of a molecule whose name we do not know. Okay, so if you follow the rules of naming compounds, there are some of you who would want to pause the video and try to come up with the name for this thing. You can do that, but the name that we get here is that this is a 2,3,3 trimethyl but1-ene. Okay, it's quite a lengthy name, and this is a type of an IUPAC name that would give you 3 marks, or sometimes even more if they were to ask you this question. Now let's get straight into it. How do we get into this name, and what does each part of the name represent? Remember, we said the name is divided into a prefix, a parent, and also a suffix. We're going to discuss that just now. Now, the first thing that we see there is what we refer to as our prefix. Now, in our prefix, what we see, the prefix is telling you what is attached and where is it attached. It's telling us what substituent is attached to the long chain or to the parent chain, and where is, in which carbon or on which carbon is the substituent attached. Okay, now in this case, the 2 and the 3 and the 3 are telling us that at carbon number 2 and at carbon number 2, at carbon number 2, at carbon number 3 and at carbon number 3, there are substituents, and those substituents, all of them have the name methyl. So the try there is to tell us that there are 3. There's 3 of them. So the comma there is telling us that this is the same substituent repeating itself more than once on different positions. The first methyl is on carbon 2, the second methyl is on carbon 3, and the third one is also on carbon 3. And then it's a methyl. So this is the what is the methyl, and then the where is where the numbers are telling you. So the numbers are telling you where are the prefix, where are the substituents, and the name then tells you what are those substituents. So these substituents are methyls. And if you look at our diagram, you'll see that at carbon number 2 and number 3, remember with this one, because we always start counting closer to the functional group. This is the functional group, that's the double bond. So we would actually start counting at carbon 1 there. This would be carbon 2, this would be carbon 3, and this would be carbon number 4. All right, if that's the case, let me put the one underneath so that we can follow. If that's the case, then that means at carbon number 2 there must be something according to the name. Indeed, at carbon number 2 we find this thing called a methyl, which then repeats itself even at carbon 3, and it repeats itself twice at carbon number 3. Hence we have 2, 3, 3 trimethyl. The tri is to show us that there are 3 of these methyls at different positions. Okay, and then we move to the parent name. Okay, we've spoken about the prefix. Now let's go straight to the parent. Now the parent name, which is the but, the black part of the name, the parent name tells us the number of carbons in the longest chain, or in what we refer to not just as the longest chain but also as the parent chain. Okay, the parent chain, which is the longest chain consisting of the functional group, is made up of 4 carbons. Okay, we did our counting and we found that this is carbon 1, carbon 2, carbon 3, and carbon 4. So the word but represents the number 4. Then the parent has 4 carbons, hence it's a but. Then we have what we refer to as the suffix. The suffix part of the name tells us what is the homologous series to which this compound belongs. This compound belongs to what we call, the in there is telling us this belongs to what we call alkenes, okay, based on the ending of the name. Okay, so these one in here represents the homologous series to which the molecule belongs. Now there's a number 1 that goes with the in there. The number 1 is telling us where is the functional group. The functional group is at carbon number 1. As you can see, there's carbon 1 and carbon 2. So the double bond is between carbon 1 and carbon 2. We always use the smaller number to represent the position of the functional group. Okay, in a nutshell, this is the structure of the IUPAC name of an organic compound or an organic molecule. It's divided into 3 parts: the prefix, the parent, and the suffix. And also you should know that the prefix is not always there. There are molecules that do not have substituents. So if a molecule does not have substituents, definitely there will be no prefix. It will only have a parent name and a suffix. So if this did not have the 3 methyls, it would just be a but 1 in. It will just be a but 1 in because it wouldn't have substituents, and therefore the prefix would not exist. I hope this makes sense, and it will also help you to be able to read the name and be able to draw the structure. So you should be able to read the name and draw the structure, and you must also be able to write the name if you are given the structure, and vice versa. So these are all the things that you need to know with regards to IUPAC naming. But now we continue. There's something that we mentioned in the previous slide. Numbering should always start from the carbon closest to the functional group. You saw in the previous slide that the numbering was done from this carbon. This is carbon number 1, and that's because there's a functional group there. We couldn't start counting here because the functional group is on the other end. We start counting closer to the functional group. But the statement here says, or closest to the first substituent or branch in the case of haloalkanes and alkanes. Okay, so if your molecule is an alkane or a haloalkane, because those ones do not have a functional group, you start counting closer to the branch or closer to the substituent. A branch being a methyl or an ethyl. A substituent can be your bromine, your chlorine, your fluorine, and so on. Those halogens that are what make a haloalkane. The other thing you should know is that in the IUPAC name, substituents are written alphabetically, regardless of their position in the chain. Okay. Now, what this means is that if you have a methyl and an ethyl, you see methyl starts with the letter M, ethyl starts with the letter E. It does not matter where the ethyl is placed in the chain. When you write the IUPAC name, you start by writing the ethyl before the methyl. Even if the methyl is at carbon number 2 and the ethyl is at carbon number 4, you'd start with the ethyl because it starts with the letter E. Hence, that's what we mean by alphabetically, regardless of the position. Now, here's another part that really confuses learners quite a bit: the separation of characters. In the name, you would find that there is a substituent that repeats its appearance on the chain. Just like with the previous example that we saw a methyl repeating itself 3 times. Because it's repeating itself 3 times, the numbers are going to repeat themselves. Hence, we are going to have a comma to separate the 2 consecutive numbers. We only use the comma to separate 2 consecutive numbers. Okay, and this only happens when you have 2 or when you have one substituent appearing more than once on the chain, which means you have the same substituent appearing at various positions on the chain. There's definitely going to be that comma there to separate the numbers when you do your naming. Then you use a hyphen to separate a number and a letter being a part of the word, just to make sure that we are all clear there. So you separate the number and the word with the hyphen, which is going to separate the prefix from the parent most of the time. Okay, there should be no separation between 2 letters or between 2 words. All right, so if there's a methyl pentane or a bromohexane, so after the bromo there starts another word, hexane. There should be no separation between the bromo and the hexane. There's no separation there. There's no space, there's no hyphen, and there's no comma there. So 2 letters are not separated, but a letter and a number are separated by a hyphen, and then 2 numbers are separated by a comma in the IUPAC naming. Now let's look at an example. Here is a 2,3 dibromo 3-methyl pentane. It's quite a lengthy name. Like I said earlier on, you should be able to look at the name and be able to draw the structural formula in particular, and also be able to move to other formulae as well. Okay, now when you are given the IUPAC name and you have to go back to drawing the structural formula, the best way is to start with the parent. There's the parent. The pent is telling us that the longest carbon chain, longest continuous chain of carbons has 5 carbons. Okay, now that's the first thing that you should do. You should then draw the first 5 carbons. Okay, so let's do that and say carbon 1, 2, 3, 4, and 5. Okay, now what do we know? I'll just put the bonds here because I see there are only single bonds. I know that there are only the only bonds that are in this molecule are single bonds, because this is an alkane. Alkanes are saturated molecules, therefore they do not have any multiple bonds between carbons. Hence, I put only the single bonds between the carbons there. Okay, now the next thing is to then go to the prefix. The prefix goes all the way here. The 2,3 dibromo 3-methyl. That's a prefix. It tells us what is attached and where is it attached. Now, this is telling us at carbon number 2 and at carbon number 3, they are bromos. They are hence the prefix di to say that there are 2 bromines attached at carbon 2 and the other one at carbon 3. So I'm going to put a bromine here. Okay, my computer is showing me flames now. Bromine here and another bromine there. Okay, that would be carbon 2 and carbon 3. But also at carbon number 3, it's not just the bromine at carbon 3, there's also a methyl. Methyl is a CH3. So this would be carbon 3, then we put a CH3 there to show that that's our methyl. Now, those are all the substituents. 2, 3 dibromo, that's 2, 3 dibromo, 3 methyl. Okay, even alphabetically they follow each other in that order because bromo comes before methyl. Even in terms of the alphabetical order, they follow each other in that order because bromo, B, comes before M, hence it's bromo before the methyl. Right, now the remaining bonds, remember, you don't stop here. Every carbon must be bonded to 4 different atoms, or they must have 4 bonds around them, not necessarily 4 different atoms, because sometimes you have multiple bonds. Okay, so which means then we're going to put hydrogens in the remaining bonds. Okay, here we only have single bonds, we don't have any multiple bonds because this is an alkane, like I mentioned earlier on. So this is basically how you would draw this 2,3 dibromo 3 methyl pentane compound. All right, let's wrap it up with some tips. When you are dealing with question 2 on paper 2, what you need to do, the first thing is to study each compound that is given to you in the statement. Guys, do not rush into the questions. I know, learners, you're thinking about time, you want to finish on time and everything, but it doesn't help to finish on time and you got the questions wrong. Rather get the questions right and finish whenever you finish. Okay, so study the compounds that were given to you first. If you know something about those compounds, write it down. Write it down, everything that you know about it, because it might be in the question. Okay, study the compounds and then write down whatever you know about that particular compound or those compounds that were given to you. Very often they'll give you a table of compounds ranging from A to G or A to F. And they are written in different formulae. This side you find that it's an IUPAC name, another molecule it's a structural formula, in another one it's a molecular formula, and sometimes you find that there are 2 molecules with the same molecular formula, and then you'd remember that those one with the same molecular formula are what we call isomers. Those are some of the things that you need to take care of when you're writing, especially question 2 of paper 2 in physical sciences. Right, we'll record another lesson on part 2, which will be on the physical properties of organic molecules. I hope you do understand. This has been Butu Academy, lessons that empower. I hope you feel empowered. Thank you.